right, so today we're going to review 4 of the sound parameters and their relationships to each other. The 4 parameters are frequency, period, wavelength, propagation, speed. Parameters are ways that we talk about and measure sound, and they interact with each other in a different way. Some of them have direct relationships, some of them have indirect relationships. So the first is frequency, and we represent frequency with this lowercase fancy f. Frequency is the number of cycles per second, and this is determined by the sound source. The transducer that we use determines frequency. So we'll talk about more about how this happens when we cover the construction of a transducer, but for now just remember that these formulas are related to the frequency coming out of the transducer, right? Nothing to do with the body yet, just frequency coming out of the transducer. The first formula that we have for frequency is 1 over period. We represent period with that capital T. The relationship is pretty straightforward. They're opposite sides of the baseline, so therefore they're inversely related. Frequency and period actually have that special reciprocal relationship where if they were multiplied together, they would equal 1. So what this means in terms of understanding how they interact is that if frequency increases, period decreases. So frequency goes up, period goes down. This makes sense when you think about it logically. If the number of cycles per second increases, then the amount of time each cycle takes has to decrease so that more cycles can pass through a certain point in a second. The opposite of that is also true. If the number of cycles per second decreases, then the amount of time each cycle takes increases. There's less cycles passing through a certain point in a second. The second formula we used for frequency is propagation speed over wavelength. Important to remember here that we're talking about propagation speed within the element inside the transducer. This is not about propagation speed in the human body. This is, in part, how we determine how frequency is determined by the transducer construction itself. So we talk about that a lot more in Chapter 2, but right now remember that this is the propagation speed of that element inside the transducer. When we look at this formula, frequency and propagation speed, the little c, are on the same side of the baseline, meaning they have a direct relationship. So if propagation speed is increased, frequency is increased. If propagation speed is decreased, frequency is decreased. Or the opposite way, right? If frequency is decreased, propagation speed is decreased. This makes sense again, right? If you think about this, if there are more cycles in a second, then speed would be faster. Frequency and wavelength, the lambda symbol, are on opposite sides of the baseline, meaning they have an inverse relationship. If there's more cycles per second, the wavelength has to be shorter. If there's less cycles per second, the wavelength has to be longer. Inverse relationship. Period is the reciprocal of frequency. So these relationships are going to be opposite of frequency relationships. The formula we use is 1 over frequency. Right? Just kind of flip-flopping that formula. You can see that they're inverse frequency and period, just like we discussed when we were talking about frequency. So if period increases, or it's taking longer for one cycle to occur, then frequency is decreasing, or there's less cycles per second. And vice versa. So if period decreases, shorter amount of time for one cycle to occur, then frequency is going to increase. More cycles per second. We can figure out the relationship between period and wavelength and propagation speed by realizing that it would be the opposite of frequency, or we can prove that through the formula. So if we're going to prove that through the formula, we are going to take our formula here, right, and we'll replace our formula here, we'll replace frequency with propagation speed over wavelength, and then solve to simplify this equation. So let's do that. So we'll do t equals 1 over that, and if we multiply out, we wind up with propagation speed over wavelength equals 1 over period. And then we can easily see that propagation speed and period are inversely related. So if propagation speed is slower, then it will take longer for one cycle to occur. If propagation speed is faster, period will decrease. It will be shorter for one cycle to occur. Wavelength and period are directly related. If period increases, then wavelength increases. If period decreases, then wavelength decreases. This makes sense because they're measuring the same thing, right? One cycle. Just wavelength is talking about the spatial measurement and period is talking about the time measurement, but they're still both talking about one cycle. So if one cycle gets longer in time, it also gets longer in space. If it gets shorter in time, it also gets shorter in space. So now when we look at wavelength, down here, the lambda symbol, we've already discussed it in terms of frequency and period. Wavelength is determined by both the source of sound and the medium it's going to travel through. So the formula that we use for this is propagation speed over frequency. And if you've noticed, right, you can really memorize just the one formula and then you can kind of use that formula to solve the others. We know that wavelength and frequency are inversely related. An increase in the number of cycles per second results in a decrease in the length of a wave. So we know that they are inversely related. We know that wavelength and period are directly related. An increase in the amount of time one cycle takes results in an increase in the length of the wave. And from the formula, we can see that wavelength and propagation speed are directly related. If propagation speed is faster, then wavelength would be longer for the same number of cycles to pass a particular point in 1 second. If propagation speed is slower, then the wavelength would need to be shorter so that the same amount of cycles can pass a particular point in 1 second. So now we also know that the average propagation speed for soft tissue is 1540 meters per second or 1.54 millimeters per microsecond. So we can actually have a soft tissue specific formula to calculate what our wavelengths will be in soft tissue when we use the 1.54 millimeters per microsecond and the frequency of the wave that we're using. So sometimes when we need a soft tissue specific formula in ultrasound to determine wavelength, we could use this formula. And so kind of a side note to know that formula as well. Propagation speed is the one that I think is the trickiest and can be a little complicated. So when we talk about propagation speed, remember it's determined only by the medium. When we talk about it in relation to sound production, we're talking about the propagation speed of the element inside the transducer. This is what has a relationship with frequency, period, and wavelength in terms of creating what sound is coming out of the transducer that we're sending into the body, okay? But we're not talking about the propagation speed in the body yet. When we're talking about those relationships, we're talking about the propagation speed of the material that's creating the sound inside the transducer. We actually already figured out all these relationships in the previous sections here. But we can also use that formula and solve for propagation speed and see them in formula form. So we'll start with the frequency formula, which is frequency equals propagation speed over wavelength. And then we'll solve for propagation speed. So solve for propagation speed. And you wind up with wavelength times frequency equals propagation speed. Propagation speed is directly related to frequency, and directly related to wavelength. Right? No inverse relationship in that formula once you solve for propagation speed. So if propagation speed goes up, frequency goes up, wavelength goes up. Propagation speed goes down, frequency goes down, wavelength goes down. And now we know, right, that period and frequency are reciprocal. So propagation speed is going to have the opposite relationship with period. Now we also talk about propagation speed in terms of the sound going through the body. So once sound's produced, we do send it into the body. And this is that number that scientists have calculated to be 1540 meters per second or 1.54 millimeters per microsecond for soft tissue. And this doesn't change based on the sound we produced. It's determined by the medium's elasticity and density. So we use the formula propagation speed equals elasticity over density. This is a really big simplification of this concept, but it's all we need for this course. So what we need to remember is that stiffness is a substitute for elasticity, and stiffness is a substitute for elasticity, and stiffness and speed are directly related, right? This direct relationship here. So if stiffness goes up, speed goes up. Stiffness goes down, speed goes down. And then the opposite is true for density. Density and speed are inversely related. I put a stiffness and a D for density here, but we use elasticity and then that silly P, that kind of like loopy P for density. So if something's stiffer, sound goes faster through it. If something's denser, sound goes slower through it. And this is independent of frequency or other parameters. This is about speed through soft tissue. Okay, speed of sound once it's already been produced, traveling through the soft tissue. This is how speed impacts the production of sound when it's in the transducer. So understanding the relationships between these parameters will be essential as we move forward in this course. I think one of the easiest ways to do this is to memorize the formulas, because when you look at them, then you can just know the relationship without having to think it through necessarily. But if you have a good basis understanding of the relationships and how when one changes, the other changes, that'll be definitely helpful for you. You could look at this and really, if you memorize this frequency formula, and if you know that frequency and period are inverse or reciprocal, right, you can pretty much, off of those, figure out most of these formulas.